Alright, welcome to Jedi Lesson 10. This is homework from week 6B on Riley Plus, and this is problem number 1. The two loudspeakers in the drawing are producing identical sound waves. The waves spread out and overlap at the point P. This situation is analogous to Young double-slit and experiment, except that sound waves are being used. What is the difference L2 minus L1 in the two path lengths if point P is the third sound intensity minimum for the central sound intensity maximum? Express this difference in terms of wavelength lambda of the sound. Okay, so first I want to start by kind of explaining what the image that was provided under us shows. So we have these lines which represent the waves that are traveling from the two speakers, which is S1 and S2. And then they reach this point, which is point P. And so then because these two paths are unequal, then the two sound waves should arrive like not in sync, basically. And so then we need to find that third minimum of where one of the waves meets the value or drop of the other, so that they could cancel each other out. So I guess to draw something well, I also define some of our important terms here. We can it's kind of difficult for me to think of other images after problems have their own, but I'm gonna try. So we have our speakers, I guess, here. Okay, this is going to be speaker 1. I'm just going to label it as S1. Okay, and then we also have speaker 2. Speaker 2. Okay, and they have identical sound waves. So when I think of identical sound waves, I think they're like the same, like that, with the same pace, same length. Okay, and then the waves spread out and overlap at point P. Okay, so I'm gonna say that we have this surface here, and point P is here. Or it's closer to S1, I guess. This is point P. And I'm gonna redraw these so that they spread out and overlap at point P. So this is coming to point P. This one is also like, I wanna come to point P too. So they meet. Okay, but also this sound wave, I should do it in a different color. Okay. This sound wave here is much longer than this sound wave here. And we can see that visually because this one is at S2, the speaker 2, is at more of an angle, more of a slant compared to S1, so that takes up more distance. Okay? So hopefully that kind of helps see this drawing in another light. And then one more thing I want to point out is they also drew the central maximum. So let's make sure to include that too. That's going to be at the point P. Like straight across. Oh, my bad. That was not a point P. That was going to be just in between both of them. That makes more sense. Okay. And then that's going to be the central maximum. Alright. So now that we have this, I want to go ahead and define some of the terms that we're going to see here. So the first one is the length of the path, which are represented by the L1 and the L2 that we keep seeing here. And that's just the distance traveled by the wave from that speaker to that specific point, so in this case point P. And that's what we labeled here, in black, the path. So those are path lengths, and the SI units for those are meters. Then we have the difference of path lengths, which is represented by delta L, and that's the difference between the two lengths that are traveled by the wave. So we know that this equals L2 minus L1. And the SI units for this are also meters. And then we have wavelengths, which is represented by this character called lambda. And that's the distance between the identical points on the wave. So they could be, which I'm glad that I drew the waves like that, so then we know that that could be the difference between, the distance between like the crest to crest or trove to trove. So it could be like there, and then that is measured in meters. And then lastly, the sound intensity maximum. Zoom out a little bit. That's the point where the overlapping waves come together, but they're also out of sync, right? So this would be point P. And the SI unit for this is watts per meter squared. Perfect. Okay, now that we've defined those terms for us, let's go ahead and get into solving the problem. So the equation for destructive interference is going to be delta L equals m minus a half, and then we have that lambda. Okay, and so we know that delta L is equal to the two lengths, the difference of the two lengths, and then m is the order of the minimum. And then we can go ahead and find the third minimum. So if we set it to m equals 3, then we can plug all those values in. So we know that delta L equals 3 minus 1/2, and then we have lambda here. And so then if we plug this into our calculator, we get 5/2 lambda. And that we can go ahead and check. And that checks out with our final answer. Alright, so we're going to go ahead and move on to the second problem of homework 6b. So it states, in a certain Young's double slit experiment, an interference pattern is formed on a distant screen. The angle that locates a given bright fringe is small, so that the approximation sine theta is approximately theta is valid. By what factor does that angle change if the wavelength lambda is doubled and the slit separation d is doubled? Alright, so we have a sketch already drawn for us, and I'm going to go ahead and draw my own, which I mentioned sometimes that gets a little hard for me, because I have to think of something to draw. But I'm gonna go based on what they've given us already to kind of get an idea, and just kind of walk through it and explain it over again to also show what they are giving us here. So this sketch shows the Young's double slit geometry, and we can see that the light passing through the slits is separated by the distance d, which is interfering, to form that bright fringe, which gives us that angle here. So we have this bright fringe here. Sorry. And then we also have this double slit here. Okay. And here. This could be the openings, the slits. Okay. This is the double slit. And so then we have this here, which is the light. I feel like the light could be in a yellow color. This is the light. Okay. And then it separated by d. We have to find this angle here, just theta. Okay. There. Perfect. This is going to be the central maximum. And then we have slit 1 here, and this is going to be slit 2. Just easier for me to know, like, differentiate them. And then our D here. Okay. Now that we have this, I'm going to go ahead and define some terms that are going to be helpful to us. So, as always, I'm going to write them here. We have the slit separation, which is represented by that D. And that's the distance between the two slits that are next to each other. And the SI units for this are meters. Then we have wavelength, which we mentioned in the previous problem, lambda here. And then we have those SI units are meters as well. Then we have the fringe order, which is seen as m. And that just shows us what bright line is being targeted that's relative to the center. So we have the SI unit for this. There's none. Okay, no units. And then last we have angular position, which is represented by theta. And then this is in radians. Perfect. So then now that we've gone over and defined some of our terms, we have this equation here. Sine theta equals m over lambda. Ooh. Lambda and then over the distance. So the path length difference has between the light coming from the two slits has to be an integer multiple of the wavelength, which is shown kind of through this equation here. And then we can go ahead and use the small angle approximation rule. So then this would be theta equals m lambda over d. And then now we can just calculate that change, and since we have, wait, 1 second, oh yeah, we can calculate the change now, so then we have lambda prime is the 2 lambda, and then d prime is 2 d, and so the new angle is going to be seen as lambda prime, okay? So we're going to have theta prime equals m, and then over lambda prime over the d primed equals m, and we can go ahead and plug in our new values, 2 and 2d, and then these cancel out, these two numerators and denominators, but then the lambda and the d stay, so that equals m lambda d equals theta. And then since this kind of brought us to the beginning, like it didn't change at all, so since the expression is not changing at all, then we know that the angular position also does not change. So that is our conclusion for this. Doesn't change. And now we can go ahead and check to see if this is correct.